should tell Rama, say by tomorrow, so that we can inform them about the exact number of people. And today's talk by Professor Lieb is on the Bose gas, a sample many-body problem. The last talk will be given on the Thursday at 4 o'clock. Okay, why don't you start?
Well, thanks again. So I want to talk about something completely different today, of course, namely the Bose gas. And some of you may not have heard of the Bose gas, but it's a subject of very great interest, both theoretically and also experimentally in physics, and it's absolutely phenomenal. Some of the things that one can actually observe that were talked about in the early days of quantum mechanics. The name Bose comes from the Indian physicist Bose, and the peculiar properties of this system, of this many-body system, were discovered, if you like, by Bose, and independently or independent, but at the same time, there was some interchange by Einstein, so it's called Bose-Einstein, if you want to be technical about it, but most people just call it Bose. Now, so these peculiar properties were invented in the early days of quantum mechanics, but nobody could see them because the conditions under which they were going to be seen did not exist at that time, or that is, could not be produced. And in fact, it's only very recently, maybe the last 5 years or so, that one could actually produce this in a laboratory. And which shows that it's technically rather hard. And many new things are coming out of this. Many new strange things. The fact that in quantum mechanics, matter is a wave, that fact which I guess everybody knows, that fact will be more and more prominent. People will make more and more experiments based on these things, these techniques, that will actually show interference of the waves that matter is. It seems almost impossible to believe, but that's what's going to happen. In fact, it's already happened. But more and more it will be important. So, that's some poetry. Let me start with some of the mathematics. But the work I'm talking about is focused. I guess it's focused. I guess that's about as good as it's going to get. Okay, so this is joint work with Robert Zaringer, who was a student of Jakob Ingwersen, and young Philip Solovey, and myself. Various people did various parts of what I'm going to talk about. So the poetry goes like this. Schrödinger's equation in 1926, of course, defined the new mechanics. I guess everybody knows what this mechanics is. And the Hamiltonian describing the mechanics is based on classical mechanics, but it actually is a differential equation, partial differential equation, and it leads to a partial differential equation. And sometimes, although the input is classical mechanics in the sense of intuition, or the sense of construction of the Hamiltonian, the output, what actually happens, what actually comes out of this, is sometimes very non-intuitive, and Bose gas is the prime example of this. So I'm going to be concerned with the lowest energy or ground state of the system. In quantum mechanics, there's always a lowest energy, or not always, but usually there's a lowest energy, unlike classical mechanics. And you might say, well, that's kind of dull, but it isn't, because almost everything we see in the world is in its state of lowest energy, in fact, or very close to it. And it's very rare that you see anything that's not very close to its lowest energy. Okay, now mathematics, you look for a function of n variables if there are n particles. So here we have psi of x1 to xn. And it will be obvious from essentially Prof-Frobenius argument that the eigenfunction of the Hamiltonian corresponding to the lowest eigenvalue, since it's an elliptic operator, will be positive as a function. And since it's positive and necessarily symmetric, the Hamiltonian is necessarily symmetric in all the variables because they're indistinguishable, the same atoms or whatever they are, they're all the same. Then, since the lowest eigenfunction is positive and necessarily belongs to some representation of the symmetric group, it has to be the symmetric representation. That's the only possibility. So, to say that we're looking for the lowest eigenfunction is the same thing as saying we're looking for the lowest symmetric eigenfunction. And the word symmetric is synonymous with the word boson. So, boson means that you're looking at the functions you're allowed to look at are the symmetric functions, but that comes out automatically. I want to emphasize that in the case of the ground state. Now, sorry, did I say something wrong? No? Okay. Now, if instead of that, this is now a footnote really, if instead of imposing that you're looking for the absolute ground state, the lowest eigenfunction, this Hamiltonian operator, which I will write down in a moment, if you say that you're looking for the lowest anti-symmetric function, which is again a one-dimensional representation of the symmetric group, but the anti-symmetric one, the alternating, then that's called, doing that is called imposing the Pauli exclusion principle. That's the name given to that. And that's appropriate for other kinds of particles, electrons. And then, oddly enough, and this is oddly, because you wouldn't expect it, the output, the results that you get when you solve the problem under the condition that you're looking at antisymmetric functions look much more classical than the ones when you don't impose this. In fact, this antisymmetry requirement, which is appropriate for these particles, antisymmetric solutions of Schrödinger's equation, are essential, absolutely essential for understanding the stability of ordinary matter. Without that, we won't have any stability. And these bosons, which are symmetric, behave in a very peculiar way. That's why this is, call this a subtle antibody problem. All right, now, in my talk on Thursday, I'm going to talk about the stability of matter, and essentially that would be this Pauli principle. But the Pauli principle is not there today. We're talking about symmetric functions. Now, again, to continue with the poetry, recent experiments have confirmed some of the bizarre properties of these bosons, that is, of the properties of this ground state. But the theoretical ideas, now, not Bose and not Einstein, but the theoretical analysis of this at a more deeper level, it goes back to the 40s to the 60s. And in fact, it starts in 1947 with Lieb, one of the most important papers in mathematical physics, or theoretical physics. Because the particles that I'm going to talk about are in fact atoms, and they interact with each other. They're not free particles, they bang against each other, even though the cases I want to talk about are cases of very dilute gases, very low density, and they only bang against each other occasionally. Nevertheless, that interaction is important, and it was Bose in 1947 who gave the first analysis of the system. And it's ever since, people, or at least some people, have been trying to verify what he claimed to be true. Because it was a sort of inspired, in many cases an inspired guess, and I'll explain a little bit later, that he made. He could not prove any of the things he said, but most people believe that nevertheless it's correct, and we've been trying for 50 years or 60 years to verify some of these things. So, some of the things that he said in 1947 have now been verified rigorously for the ground state, or at least for the ground state energy, for the lowest eigenvalue. Energy and eigenvalue are the same thing. So for the lowest eigenvalue of the Schrödinger operator, some of those things have now been verified, and that's what I'm going to talk about. So now, I say 3 or 4 decades, actually starting from Bogoliubov, it's more like 5 decades, but in the 50s, people expanded on Bogoliubov. Again, it was still non-rigorous, but clarified the situation very considerably, but still the situation remained as no one was able to justify the essential steps in the analysis in the 50s. And then it was a bit like, well, like the Americans with the Vietnam War, we just declared that we won and we got out, and that's what those people did. They said, well, problem is solved, and we're going to drop it. But of course, it wasn't solved. And it becomes important now because there are actual experiments, as I said, that actually verify some of these things. Now, there are 3 topics that I will talk about. The first one with Jakob Ingwersen is a dilute gas of these things, and they're repulsive, so these particles bang against each other like that. They don't attract each other, they repel each other. Think of them as hard marbles. That's a good case. And the density is very low, and we're in either 2 dimensions or 3 dimensions, and there's a difference, an interesting difference between the 2. And then this gets modified with the help of Robert Zeiringer through bosons in a trap. That is to say, what you actually do in these experiments is you put this gas of atoms in a little very cool chamber, and they rattle around there, you see what they do, and that requires some modification in the mathematics, and that's what this is about. And the equation that's supposed to govern that, oops, I have one quotation mark, but not the other, is the Gross-Pitievsky equation, which was discovered independently by Gross and Pitievsky, and with different justification, I might add, but anyway, there it is, it's this equation, and that's the thing that people use, and the problem is to justify it. Finally, there's some very recent, or really recent, so recent that it hasn't been written up yet, just a draft, with Solovay on the Mendelian model. So now we're talking about charged particles instead of little hard marbles. These are charged particles. So the interaction among these Bose particles is now very long range, the Coulomb forces, 1/r potentials. And the case that is supposed to be covered by Bogoliubov's theory, which was analyzed by Foldy in 1961, in that case is supposed to work at high density rather than low density. So this is high density. And this is the first time that the actual nuts of the Bogoliubov theory have been shown to be right. Here is only the leading term that was shown to be right. But in this case, since it turns out there's no leading term, the leading term is trivially 0, the first interesting term is the second order term, and that's where Bogoliubov's theory about the Bose gas really comes into play, and that's the first, as far as I know, verification of that. So let me start with the, oh, I should put this here. This is 4, so I can do that. Except it's out of focus. We do what we can. All right. So now I will explain what the Hamiltonian of the system is. So the Hamiltonian is a partial differential operator. It acts on functions of n variables. Each xi is in R3. And so it's a function of size of x1 up to xn. And it's the following operator. It's the sum from 1 to n of the Laplacians acting on all these variables. So it's just the Laplacian times a constant, u. And some pair potential, some v of xi minus xj, and this n particles, and n is a very large number. The volume is also a very large number. The volume is L cubed, and the ratio is kept fixed at some number, some small number, but fixed. You take larger and larger parts, more and more particles, and you put some boundary conditions on the walls of the box, and then each n hits the walls of the box. The boundary condition is not important. Because in this limit of a very large box, it doesn't matter whether you use Neumann boundary conditions or Dirichlet, it really doesn't matter. This is pretty well understood. And this constant in front is Planck's constant squared divided by twice the mass of these atoms and particles. Okay. Now in the trap case, we add, which I'll talk about later, we add this external potential, a sum of some given V, not to be confused with that V, some potential depending on each variable, sums from 1 to n. So that's the V that holds everything together. But here, it's the walls of the box. There's no V. And we're going to ask you about the ground state energy, the lowest eigenvalue of this thing, which, as I said, will correspond to a symmetric function, necessarily, because it's a positive function. And we're interested in this energy. Here it is. It's a function of n and V divided by n in the limit, and that will be some function of rho. This has to be proved that this limit exists. So there's really a limit involved here. It has to be proved that that limit exists, but we know how to do that. That's an old story. So you just take that as read. Okay. Now, what Lieb said in 1947 was that the leading order in rho, the density is very small. It's a very dilute gas. So the volume V is very large compared to n. This energy per particle is this constant. Beg your pardon? I'm sorry?
Question 1 means dividing by u on the right hand side, not multiplying by u.
No. No.
Oh, u is not the mass.
U is 1 over the base. U is h strokes squared over. So it's supposed to be mu times that u up there, times 4 pi times the density times A. What is A? A is a magic number. It's called the scattering length of this potential, but I will explain later what this is. Anyway, so it's some number which is characteristic of the potential V, and also it depends on mu. Usually people forget that. That's why I'm putting the mu in there. Usually people write 4 pi rho A, and they say A is the scattering length, and we're using units in which mu equals 1, but this is not a good idea. There really is a hidden mu dependence in here, in fact. So it's best to keep all the constants, but you don't see what's going on. Okay, now I will explain what this A is. So it's some number characteristic of V. This is what Lieb wrote down. This is the leading energy. And there were several alternative derivations of this in the 50s. But the question is it right? By derivation, of course, we mean physicist derivation. Oh, yes, thanks. I'm glad you reminded me. I appreciate that very much. Because I tend to forget. I have always good intentions to do this, and then I forget. I really appreciate it. Okay. So Dyson found a bound. And you'd like to get an upper and lower bound to see that that answer is correct. I mean, poetry is one thing, but mathematics is another thing. Now, the case that Dyson considered, which was the case that everybody else was considering, was where this little v of x is the function. I'll write it down here. There's a piece of chalk. The hardcore case, so-called, where v of x is equal to infinity if x is less than a. It's the same a that I've been talking about there, and it's equal to 0 if x is bigger than a. So it's very big at 0. So it's a hardcore. Particles cannot penetrate each other. And in that case, you got this formula as an upper. You got an upper bound for the energy, for the lowest eigenvalue, and to leading order, this was correct. So this is fine. But the best lower bound he was able to get in 1957 was 14 times too small. And if you want to know matter stood until 1998. There were no other bounds. People tried. And the fact that something as simple as this, which is supposed to be obvious almost, could not be proved, but really somehow indicates that this is a subtle problem. And I'll explain why it's subtle, what the difficulty is. So, there are usually upper bounds are easy to get by just the variational principle. But even to get the upper bounds is a subtle problem. And Dyson had to work very hard to get that upper bound. It was not easy. Anybody who knows Dyson knows that he's one of the cleverest people there is. And it really took a lot of pages to get that right. It was not easy, but he got it. But now what we need is a lower bound, since we have the upper bounds, thanks to Dyson. So we just have to get the lower. Now, why is this a difficult problem? Well, let's assume for the moment that this answer is right, or something like it. Assume that it's right. Then, by the Heisenberg uncertainty principle, or the Sobolev, or whatever you want to call it, this energy, rho A, that defines a length. The length is 1 divided by the square root of rho A. That's the length, so that if you try to localize something with the Laplacian, the kinetic energy, it has to be that big. So you cannot squeeze the particles in a distance smaller than something of this order, if that's the right answer, because if you do, you'll get the energy will be too big. Now let's call that LC. Assuming that's the right answer, that defines a length like this. On the other hand, the mean particle spacing, if you have a gas just from geometry, is rho to the minus a third. That's the mean distance between the particles, which are around at random. Rho is the density of the particles. So there's a dimensionless number, let's call it y, which is rho A cubed. Rho has the dimensions of 1 over length cubed. A has the dimensions of the length. In this case, it's that length. And by the way, in the experiments, it's a very small number. It's about 10 to the minus 6. So it's a good idea to try to expand things for small quantities. Now, this number, this uncertainty principle length, 1 over square root of rho A, can be written as this number to the power minus a sixth times rho to the minus a third. And that, since this is small, that number is much bigger than that number. In other words, you have the following problem. If the answer is correct, you cannot localize the particles in a distance that's small compared to their mean spacing. This length over which you have to let the function be more or less constant, you don't want to get too many ripples in it, and therefore too much gradient energy. That length has to be much bigger than the mean spacing. And there's no way you can think about this situation classically. Not at all. See, somehow a particle has to live over a distance in a certain poetic sense that's much bigger than the distance to its neighbor. On the other hand, its neighbor is sitting there with a potential B, which might be this hard core. So this particle, let's look at a typical particle, it has to somehow have a very smooth function. So its Fourier transform has to be largely concentrated near zero, like k equals 0. But it has to have these little holes in it. Because if it didn't have the little holes in it, it would pick up infinite energy. So it has to have these little tiny holes. But the holes somehow shouldn't bother it too much. And all the holes leave over is this energy which corresponds to that length. It's very mysterious. Now, if you don't understand what I said, that's okay, because it's, well, it is hard to understand. And for fermions, the situation where you have the anti-symmetry, where you look for anti-symmetric functions, and this is something I'll talk about on Thursday. For fermions, this length, that you would get if you had the correct energy for fermions, for anti-symmetric functions, this is for symmetric functions, the corresponding length would be of the order of the density to the minus a third. In other words, would be of the order of the mean space of the particles. So fermions are much easier to talk about. So, but I won't say anything more about fermions. Now, suppose you use perturbation theory. There's an operator, and let's say that this is what Bob said. Suppose we think that V is very weak. So the first order, the lowest eigenfunction of that operator is just the lowest eigenfunction of the Laplacian. The lowest eigenfunction of the Laplacian is the constant function, except for the box one. It's not the box is far. The walls are far. So if you forget the V, then the lowest eigenfunction of n variables, here it is just a constant, and it's normalized by dividing by the volume to the minus n over 2. That's just to normalize it in L2. It's the constant function. And then if you treat the little v term as a perturbation, what you do, you would just compute the expectation value of that little v with this function. That's what you would do. And you would come up with this answer, divided by n, namely the energy per particle would come out to be, if you did the calculations, very easy, 1/2 the density times the integral of this little v. That's what you would get. And that's called perturbation theory, and it's clearly wrong. Because, for example, if v is this hard core, the integral of v is infinity. And does not agree with what's written over there. But then, so Bogoliubov got this result, and then there's an interesting footnote in his 1947 paper. He says, I got this result, it's wrong, but it's what comes out of perturbation theory, so I went to Landau. What did Landau say? Well, Landau said, well, it's not so wrong, because this number is the first approximation, one so-called water approximation, I won't explain that, to the scattering rate. So what you should really do is, that's the number that comes out, but it's the wrong number, but it's really telling you what the right answer is, namely, replace that number by 4 pi n. So, do it. So that's what Bogoliubov did. And that's black magic, because it's not, well, for 10 years or so, 15 years, people tried to justify it, and they did it in one way or another, but there was no sort of rigorous justification of this. So what is this magic number A? Well, A is the following number. If you look at the Schrödinger equation for a single variable, and here I'm writing the absolute value of x is r, so r is the distance from the origin. And you try to solve the Schrödinger equation. Here's the Schrödinger equation. Minus mu times Laplacian for one variable times psi, plus 1/2 the integral of b psi, I guess I'll leave that out, is 0. You try to solve this equation. Now, outside where the potential lives, this term isn't there, so Laplacian psi is 0, so psi is a harmonic function, and there are only two harmonic, spherically symmetric harmonic functions, the function 1 and the function 1 over r. So psi has to be a linear combination of those two things outside where the potential lives, no other choice. R0 is what I'm calling the support of this little v. So I look for psi's, try to solve this equation, look for psi's that have this form with a 1 here. And the coefficient over here I call the scatter rate. That's what it is. That's the definition of the scatter rate. It's the coefficient of the 1 over r. Now this number A depends on mu, of course, because mu enters the equation. If you take the hardcore case, which I wrote over here, then this is what psi is. And, no, actually, I'm sorry, this is psi divided by r. Psi times r. So anyway, this is the solution. And the A there is the A there. They agree, but for other V's they would be different, but in any case it's well different. Now, there are two regions to consider. One is where the V is very large, like this hardcore thing. In that case, this energy is largely coming from the first term, not the second term. And in that case, the scattering length, as in this hardcore case, is independent of mu. scattering length A turns out to be essentially 1 over mu if you analyze the situation. And thus, this number, this, if it's correct, is essentially independent of mu, because A is 1 over mu times mu is 1. And that tells you that all the energy is coming from the second term, not the first term. So two very different regions. That formula does not distinguish the two regions. It's one formula that works in two regions, which is kind of remarkable, if it's true. Now, there's something else called Bose condensation, which is very important in these experiments too. But I will not go into that. And it's not clear whether Bose condensation, or I will mention that, whether that distinguishes these two regions. Anyway, here's the theorem that we finally proved in 1998. So, I take a general potential, little b, and I define y to be the density rho times a cubed. A is the scattering length of this little b. B is non-negative. The statement is that we have the following lower bound, regardless of what little b is, as long as it has complex support. 4 pi rho a times mu, which was the conjectured answer of all the Newhoff. This is a lower bound now, times 1 minus this y to some small power, minus 5 to 1/17. This is a lousy bound. I mean, the next term really shouldn't look like that. It's pretty bad, but that's the best we can do. Anyway, that's enough to prove that the first term, mu times 4 pi rho a, really is correct. The idea of the proof is to take this big volume and break it up into lots of boxes and of fixed size and a little l, and then put Neumann boundary conditions on these boxes, which gives you a lower bound if you do that. Now, the boxes, that makes the boxes independent, but the energy has to be minimized with respect to how many particles you put in each box. You still have this free choice. And this one has to prove is whether the particle number in each box is approximately constant. In fact, is constant. It's the same sprinkle of particles with equal amount in each box. It turns out that the optimum L to choose for the size of these boxes to play this game is something that's much bigger than rho to the minus a third, which is the mean particle spacing, so these boxes will contain a lot of particles, but much smaller than this characteristic Heisenberg uncertainty principle length that I mentioned before. And then with that choice, we can prove everything we want to. Now, there's an interesting lemma of Dyson, which I'll just briefly flash in front of you, which plays a key role. It's a strange lemma, but very useful. Really weird. And I mean, it's something that only Dyson could think of. You wouldn't think of going in this direction, but it's a wonderful lemma. The dilemma is the following. Take any function you like, capital U, with the property that it's non-negative, and it's 0 if it's a function of radius, for radius r smaller than the support of this potential. So the potential sitting in here, u lives outside where the potential is. Otherwise, and yes, it has this normalization. That's all. So this potential could be this hard core, and u could be the constant function outside. So very flat, for example. Now take any star-shaped region with respect to the origin. It doesn't have to be symmetric in any sense, but it contains the origin. It's star-shaped. For example, convex. And then, for any function whatsoever defined in this star-shaped region, in any u satisfying this property, the following inequality is true. Essentially, the energy of that function phi, which is the integral of mu times the gradient of phi squared, that's the Dirichlet energy, and this is the potential energy. That energy is bigger than or equal to mu times the scattering length of the potential, and the other place the capital U comes in is mu times phi squared. So, and the proof, well, the proof Dyson gave was a little bit awkward, but the actual proof is integration by parts. So this is this. Well, that lemma of Dyson is important, and is that the ground state of the Neumann-Laplacian is the constant function.
What do you have out of here in the formula?
That's the support of the potential. So this, maybe I can make a picture here. So, if I can do it. So, here's R, distance between the particles. Here's the potential d of R. So it's some function. It's non-negative. And R0 is its support. After that, it's 0. That's the definition. Potential is otherwise completely arbitrary. And U, this U that is in that theorem, that implies U has to live outside here. It's not allowed to live in here, but otherwise it can be anything you want. And this business about having a compact support, this is a technicality, won't get around that. But okay, so now in the usual Bose theory of 1947, for people who are familiar with it, you talk about something called a condensate. And what is going on is that the ground state of the Neumann-Laplacian is the constant function in these boxes, and that's what's taking the place of the condensate. Now, the big advantage of the small box over the infinitely big box is that the Laplacian has a spectral gap, which is L to the minus 2, where L is the size of this fixed small box. And it's this fact that permits us to prove that most of the particles in this, with the Neumann boundary condition on the walls of the small box, are in fact in the lowest eigenstate of the Laplacian, the constant function, the constant function state. The corresponding assertion for the big box is called Bose condensation, and nobody knows how to prove that, because for the big box, there's no gap. But for the small box, we can prove it, and that's enough to give us the lower bound, which is there. And but everything Bogoliubov did and everything everybody else did was based on the idea that you had this condensation into the lowest eigenmode of the Laplacian. Nobody knows how to prove it, and that's why there was no proof until 1998. And when it was realized that you really didn't need this condensation in the big box, it was enough to have it in small boxes if your goal was to prove a lower bound like that. Okay, so that's the. So for the future, if you like, what we would like to prove, I'll go through this very quickly, is that to get the next term in the density, after that, what I've written there is 1 minus something is wrong. It really should be 1 plus something. It's really badly wrong. I mean, it's enough for the theorem, but the correct second term has a different sign, and it's a different power, and there are conjectures as to what it is, but we don't know how to prove it. That's the second order term in the Bogoliubov theorem, but we don't know how to prove that. The second thing what we would like to prove, as I said, is this Bose condensation, which people see in experiments. And what that says is, in mathematical terms, is the following. If you take the lowest eigenfunction of this Hamiltonian, this differential operator, Schrödinger operator, suppose you know it, it's a positive function. And let's do the following. Let's take the first, write it down twice, and take the first variable different, x and y, x and all the subsequent variables the same, and then integrate over everything. So the n plus 1 integrations here. Now, if you put the first variables equal and integrated, so you have only 1 integration, then by definition, by the normalization condition, this interval would be 1. But we're not doing that. We're making the variables different and integrating. And that number ought to be of the order of the volume, this big volume in which all these particles are sitting. And we know how to prove that. If that statement is, by order of V, I mean it really is not 0 times V. I mean this, not in the mathematician sense, but in the physicist sense, that it's a non-zero constant times V, what's meant here. The only case where it's been proved up to now, after all these years, to be true is in where you do a lattice. That means you replace R3 by Z3, and where the number of particles you're talking about is exactly half the number of sites in the big chunk of Z3 that you take. Which one are you speaking of? This
Right,
one? Yeah.
this last one. I mean, it seems that would be bounded by the L2 norm.
No, take the constant function. See, there's one more integration. Each integration essentially gives you a volume factor. Because you're integrating over this big. So you've got one more integration. I know what you're thinking, but what you can do with Cauchy-Schwarz, that's what you're thinking, is you can prove that this is less than 1 times B. You can do that. But this, all right. So this is what people think they see in the experiments. That there's this tremendous coherence. But anyway, that's for the future. Now, let me remark very briefly about 2D, 2 dimensions. This is an interesting formula, the one that we just derived. 4 pi mu a, let me write it down. So I was saying that the energy per particle, E0, which is the total energy divided by n, always take the limit n goes to infinity. This is equal to 4 pi mu rho a, essentially, to leading order. This is what I've been talking about up to now. So I've just written it down again. So big E0 is the n, so put the n on the other side. Okay. Now, if I look at this, rho is itself n over v. So this whole thing is 4 pi mu, but let me write it as 8 pi mu, if you don't mind, times a times n squared over 2v. I haven't done anything. And n squared, since n is large, is the same dimension as n minus 1. So, what this formula is telling you is that the energy is this number times the number of pairs of particles. Because that's the number of pairs there are, if you have n particles. Sorry, excuse me, put the v here. This is the number of pairs. And what is this? Well, this turns out to be the energy you would get if you just had 2 particles in the whole world in this enormously big box. The energy would go as 1 over v times the scattering rate. This you can easily conclude. So you get the energy for 2 particles times the number of pairs. This seems to be sensible. In 2D, the remarkable fact is that this isn't true. In fact, it can't be true. In 2D, there's an analog of the scattering length. You again solve this equation, but the harmonic functions are either the constant of the logarithm, only 2 harmonic spherically symmetric functions in 2 dimensions. So the psi has to go as log r over a for some number a, and that's called the scattering length in 2 dimensions. Now, the density rho in 2 dimensions is n divided by L squared, because it's 2 dimensions, not 3. The rho already has the dimensions of 1 over a length squared. Notice that rho A has dimensions of 1 over a length squared. A has the dimension of a length. Rho has the dimension of 1 over a length cubed. So in 3 dimensions, it's 1 over a length squared. It should also be in 2 dimensions because the Laplacian has dimensions of 1 over a length squared. So rho itself already has dimensions of length squared. There's no rho for the A. If a formula like that were true, it would have to be true without the A, because by dimensional analysis. So there's no room for the A. And that's ridiculous, because then you would say the energy is some constant times rho, no A. The answer wouldn't depend on A. It wouldn't depend on the potential. Turns out that the correct answer is 4 pi rho. You have crossed out the A, but you have to divide by the logarithm of rho a squared. That's the right answer. That's the energy per particle. Now this is much larger than the energy that you would get if you just put 2 particles in a big box, as it was true over here. If you put 2 particles in a big box, you would get, the rho would be 2 over L squared. Get this, which is fine, but you would get a squared over L squared. Here you're getting a squared times rho, and a squared times rho is much bigger, much smaller than L would be the leading term here. We have absolute value than A squared over L squared. So this number up there is much bigger than the number of pairs of particles times this number. So the intuition that this lowest eigenvalue is the number of pairs of particles times something is wrong. And it's very odd that this was not noticed until 1971. It's sort of amazing. It was done by a gentleman named Schick, and we proved this now last year. This is the correct answer. And the reason the logarithm comes in is that Dyson's inequality, everything that depends on his inequality, has to be modified in the case of 2 dimensions. This was the condition on U in 3 dimensions, and now has to be modified to this. So, well, that's just a fact. And that's what the logarithm comes in. So this is proof. Now, the next step is to put...
In terms of your intuitive description before, you had in 3D, at least in terms of the energy, it just looked as if you could take pairs and add the...
That's right.
But in 2D,
It's not true.
So what is the corresponding velocity? The particles interact when they're still far away?
Well, it's because of this logarithmic fall-off or non-fall-off that you have in 2 dimensions. I mean, it really comes from the fact that in 2 dimensions there's no harmonic function, well, except for the constant, that goes to 0 to infinity. In 3 or more dimensions you do, you don't in 2 and you don't in 1. But you would think that 2 ought to be more like 3 than like 1, because in 2 particles can go around each other in a scale. So you would think intuitively 2 is sort of like 3, until you realize that the Laplacian doesn't have an isomorphic function. It's just too bad that it doesn't. And that's where the trouble is coming from. Exactly. So it's really a mathematical trouble, and the physical intuition is violated. Now, when we put on a trap, that is, we don't just put particles in a big box, we put them in a small box with a potential, like going like this, that keeps them confined there. So we're now in the whole of R3 instead of in a box, each variable. But this is V, and V you should think of as going to infinity. And now, associated with this problem is the following functional, which is called the Gross-Pityevsky functional. So I take a function of 1 variable, call it phi. So now a function of 1 variable, not n. And I integrate over the whole of R3, first of all the Dirichlet energy, mu times grad phi squared. Then I take this V times phi squared over the whole of R3. And then I add to that 4 pi mu A times phi fourth. What is that doing there? Well, you should think of that as phi squared times phi squared. Phi squared is the same as that phi squared. The first phi squared is the rho. It's the density. Think of the formula up there where you replace rho, which is the density by phi squared itself, and you're led to this function L. And the subsidiary condition that you would impose on functions, apart from all the obvious ones, is the normalization condition that the integral of phi squared is n. Well, that leads you, of course, to a non-linear kind of Schrodinger equation. And you try to minimize that in an obvious way. And there's a minimizer, you can prove that. Usual methods, it's very easy. So there's a minimum to this, and therefore minimizing energy, which I call the Gross-Pityevsky energy. Depending on n. N is the Pearson's normalization. And A is the scattering length, and everything is the same as before. And what I'm doing is I'm taking that energy and trying to use it to describe what happens when I put particles in a potential like this instead of a very big box. And so this is what people actually use. And the question is this true? And, well, let me just skip ahead a little bit. We expect that this Gross-Pityevsky energy that we get minimizing that thing, ought to be equal to the lowest eigenvalue of that Hamiltonian up there in the box with the potential in the trap with the potential in the suitable limit. That's what we would expect. That's what everybody expects. Now, there are trivial limits that you can impose, but the interesting one is where all three terms, see there are three terms in that function now, where all three terms are comparable. One is not much bigger than the other. That's the interesting case. And that case corresponds to essentially saying you let n, the number of particles, so to speak, be equal to 1 divided by the scattering length. In other words, you think of the scattering length as a variable. If you want to think of the scattering length as fixed, because the potential little v is fixed, but you let the number, you won't put in too many particles. This is not bad, because experimentally, the number n is about 1 to 1,000 times 1 over a. So this end of things is correctly described by that function. Well, so is this n too, but it's kind of trivial, because the first term then disappears with this, and it's 1,000 times a. So the question is this right? And the theorem, which is that it is right, the quantum mechanical energy divided by the gross Pivievsky energy that you get from that function is the limit n goes to infinity with a going as 1 over n is 1. That's the theorem. And as I said, if you fix a instead of letting it go as 1 over n, so that the number a1, which is defined to be n times a, goes to infinity, but at the same time you let the average density times a cubed go to 0, then what this boils down to is just throwing away the first term, and that's sort of trivial. It's called the Thomas-Fermi theory, and that's easy to do, so it's not interesting. What's interesting is the theorem that's written here. Moreover, the density that you get, this gross Pivievsky phi, that you compute, when you compute the minimum, is in fact the limit of the quantum mechanical density equals n goes to infinity. Now let me not go through the proof, even the outline of the proof, because I'm running out of time a little bit. So I want to skip to the very last topic, which is this work with Solovec, and just describe that a little bit. Here, what you do is something completely different. The setting changes abruptly. Instead of particles interacting with this short-range potential compact support, they interact with the Coulomb potential. So the little v up there becomes the Coulomb potential. Let me remind you what the Hamiltonian was, which was way back here. Sorry, here it is. So it's the same. In a big box, the little v is now the Coulomb repulsion among particles. It does not look like that. It looks like a normal particle. Okay, now we take a large box, we put n particles in as before, the box has volume n cubed, the density is n over l cubed, and everything is the same as before. Now, if that's all I had, then the particles would go to the walls of the box because this Coulomb potential is so strong, you just push them all away. It's additive. So the force on the potential that one particle sees would be order n. They can't escape from each other. So in order to prevent that from happening, what we do is we take this very, very large box and fill it with some charge of uniform density, rho, the same number of rho. Just fill it with charge, a uniform negative background, the original particles are positive, so that the whole system is now neutral. So the Hamiltonian then becomes the Coulomb repulsion, kinetic energy is before, but there's some extra terms. Here's this V, this one particle V, which is the Coulomb potential generated by the negative charge in this uniform background. So it's the integral over the box, this big box, of 1 over x convolved with the characteristic function of the box times the density. And then there's a constant term, which is the interaction of the box with itself. Because you have charge in this box, it itself has which is this number, this potential, times the number of particles. I'm sorry, I should have put a row here. Okay, so now why is this interesting? Despite the fact that the Coulomb potential, the 1 over x, as everybody knows, as a kernel, as an integral kernel, is positive definite, each particle, particles in background, interact only with the other particles, not with themselves. And so the total energy, these three terms, this plus this, which is the total electrostatic energy, this can be negative, because we don't include the term in which each particle sees itself. Even though you might think it ought to be positive, it isn't. So the energy, the Bose eigenvalue of that operator can be negative, and indeed it is negative. All you have to do, for example, is times the constant function, and you see this right away. And the interesting case is where the density is large, not small, large, because it's in this regime that the particles sort of look like the background, they sort of spread out. And each particle cannot follow any other particle because there are too many of them. And you might expect some kind of perturbation theory to work in this regime. And that's what Foldy did. He took this Bogoliubov theory and followed it. So perturbation theory turns out to be correct to leading order. If you compute the expectation value with the Hamiltonian, which is there, of the constant function, you get 0, because the particles just cancel the background. So the leading term, which we were struggling with before, is 0 in this case. It's the next order, 1 over the density, that's interesting. And this is entirely due to Bogoliubov's theory. See, in a certain sense, the thing we were doing up to now has been trivial from Bogoliubov's point of view. Now we're getting into the bigger things. The leading term is 0, throw it away, and now we're looking at the correlations, which Bogoliubov dealt with. And in 1961, Leslie Foldy did exactly this. He said, let's take this Bogoliubov theory. There's no poetry anymore. We'll just turn the crank and see what we get. You don't have to call Landau. You just do it. Now, that whole theory of Bogoliubov, of course, as I said, was not correct to leading order, but here it might be correct, because we're at second order. And is this true? So this would be the first time we really seriously look at the second order Bogoliubov theory, the interesting theory. And this is my last view graph, and I'll just finish in time. If you look at this Bogoliubov theory in 1947, what he says is that the main contribution to the energy, to the lowest eigenvalue of that field, or anything of a similar kind, comes from pairing of particles into momenta k and minus k. I will explain in a second what that means. This is the analog for bosons of the Margin-Cooper-Schrieffer theory of superconductivity, which got them the Nobel Prize, which is exactly the same idea, except it came 10 years later. And Bogoliubov had it in his hands, except he didn't realize it. And after BCS published their theory, Bogoliubov went back and said, aha, I have this already. But of course he didn't. He had the mathematics, but he didn't realize that it would also give him superconductivity. He was interested in superfluidity, which is true of bosonic systems. And it's a great pity because he really had the idea first. Now, what does it mean to say pairing into particles of pairs of k and minus k? Well, it means you take a germ like this, take two variables, xi and xj, those are coordinates of two particles, any two you like, and take the exponential of e to the ik dot xi minus xj. That's a function of two variables. think of that as a germ and take products of things like that for all the different pairs of particles, as many as you like, and add them up. Not being poetic about that, but that's essentially what it is. And if you do this in a nice way, according to what we want, you'll get the right answer to leading order. You have a very definite formula for doing this. Now, the Foldy calculation yields an upper bound, turns out. This Bose method can be converted into a variational calculation. So upper bound is okay. The question is to get the lower bound. And that's what we have done now. And the answer, this is Foldy's answer for large rho, which he got as an upper bound, following Lieb. Here it is. And this is something we can now prove as a lower bound. You can get this formula, plus corrections, of course. And as far as we know, this is the first example in more than one dimension in which you can actually see into the Lieb pairing theory and actually see that it's giving you the right answer, non-trivial answer. The energy comes out as the density to the 1/4 power, which is really mysterious. But that's what it comes out to be. And so that's what we're writing. So
That's only dimension 3? Huh? Sorry, it's dimension. In what dimension?
yeah, in one dimension, yes. If you look at the delta function Bose gas, it turns out Lieb's calculation is right. It has no right to be right, but it is right. So